Somewhere out past the orbit of Neptune, a small frozen world holds a glacier shaped like a heart. This is why a planet doesn't have to be large, or warm, or familiar to hold something that stops you in your tracks. Because the same rule seems to apply to nearly every world in this solar system and beyond it, each one hiding a detail stranger than the last. And tonight, we are going to move slowly through as many of those details as we can find. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. Uranus does not spin the way the other planets do. Every other world in this solar system rotates more or less upright, spinning like a top standing on a table, but Uranus lies almost completely on its side, rolling around the sun like a ball instead of a top. Nobody is entirely certain why, though the leading idea is an ancient collision, some long-forgotten impact early in the planet's history that knocked it over and left it tilted for good. Because of that tilt, the seasons on Uranus are unlike anything a person standing on Earth could ever experience. Each pole spends roughly 42 years bathed in constant sunlight, and then swings around into roughly 42 years of unbroken night. A child born at one of those poles during the long summer would grow into a middle-aged adult before ever seeing a single sunset. Then the darkness would come, and it would stay, season after season, for a stretch of time longer than most human lifetimes used to last. The atmosphere responds to this strange rhythm in its own way, with faint methane clouds drifting through a pale blue-green haze, and winds that pick up speed as the planet slides toward its long equinox. Voyager 2 passed by Uranus only once, briefly, and much of what we know still comes from that single quiet flyby decades ago. It remains the only spacecraft ever to visit, which means this sideways world, spinning through its slow decades of light and dark, has mostly been left to turn in private, largely unwatched, drifting through its own version of time. Venus looks almost like Earth's twin from a distance, similar in size, similar in mass, wrapped in clouds that once made early astronomers wonder if it might be a lush, humid world underneath. It is nothing of the kind. The surface temperature stays hot enough to melt lead, hotter even than Mercury, which sits far closer to the sun, because Venus is wrapped in a thick blanket of carbon dioxide that traps heat and never lets it go. The clouds themselves are not made of water vapor but of sulfuric acid, drifting high above a surface where the pressure alone would crush an unprotected visitor almost instantly. And then there is the rotation, slower than anything else in the solar system, so slow that a single day on Venus lasts longer than its entire year. Stranger still, Venus spins backwards compared to nearly every other planet, so if the clouds ever parted and someone could stand on that scorched surface, the sun would appear to rise in the west and set in the east. Some scientists believe an ancient collision may explain this backward spin, much like the tilt of Uranus, evidence that violent early encounters shaped this solar system far more than the calm orbits we see today would suggest. Every spacecraft sent to land on Venus has lasted only a short while before the heat and pressure ended its mission. Brief transmissions from the surface of the closest thing our solar system has to a world built entirely of extremes. Near the North Pole of Saturn, there is a storm shaped like a hexagon, 6 straight sides meeting at 6 corners, spinning in place as if drawn with a ruler rather than shaped by wind and gas. It was first noticed decades ago, and it has held that same geometric shape ever since, wide enough to fit several Earths inside its outline, with jet streams racing along its edges far faster than any hurricane on our own planet. Scientists have recreated similar hexagonal patterns in laboratory tanks of spinning fluid, which suggests the shape comes naturally from the physics of a fast-rotating atmosphere, meeting the right kind of internal current. rather than from anything mysterious or unexplainable. Still, seeing it is another matter entirely. Spacecraft images show a golden-brown hurricane wall locked into 6 perfect corners, rotating for as long as we have been able to watch it, undisturbed by the storms and turbulence that swirl around it elsewhere on the planet. Deep inside that hexagon sits another storm, a swirling vortex at the very pole itself, glowing faintly in infrared light. A storm within a storm, layered one inside the other, like something built rather than grown. Saturn's poles remain some of the strangest weather systems we have ever observed anywhere in this solar system. A reminder that even gas giants, vast and mostly formless, can settle into patterns of astonishing and lasting order. Jupiter's great red spot has been swirling for longer than anyone has been alive to watch it. A storm larger than Earth itself, spinning counterclockwise in the planet's southern hemisphere for at least the better part of 2 centuries, and possibly far longer than that. It is an anticyclone, a high-pressure storm with no calm center the way hurricanes on Earth often have, just endless rotation, its winds tearing along its outer edge fast enough to circle the storm's own boundary in about a week. What keeps it alive for so long remains a genuine puzzle, since storms on Earth dissipate within days once they lose their source of warmth and moisture. On Jupiter, with no solid surface to create friction and slow things down, a storm like this can apparently sustain itself for centuries, feeding on the deep heat and turbulence of the planet's thick atmosphere. And yet, it has been shrinking. Measurements going back many decades show a spot that was once wide enough to fit 3 Earths across, gradually narrowing over time until it can now hold barely more than 1. Nobody is certain whether it will eventually vanish entirely or simply settle into a smaller, more stable shape, but for now, it continues turning. A colossal storm of ammonia, ice, and unknown red-tinted chemistry, drifting slowly across the striped bands of the largest planet in this solar system, patient and unbothered by the passage of human history below it. Mercury is the closest planet to the Sun, and it is also, strangely, a world of true extremes in temperature rather than simple, uniform heat. During the day, with almost no atmosphere to hold warmth or spread it evenly, the surface can grow hot enough to melt certain metals. Then night falls, and because there is no blanket of air to trap that heat, the temperature collapses within hours to hundreds of degrees below freezing. The swing between Mercury's day and night is larger than anywhere else in the solar system, a planet that cannot decide between fire and frost because it never holds on to either one. And yet, in the deep shadows of craters near its poles, places where sunlight has never once reached, scientists have found something unexpected: ice. Frozen water, sitting quietly in permanent darkness on the hottest world by proximity to the sun, protected simply by never being touched by light at all. Mercury also moves faster around the sun than any other planet, completing its orbit in under 3 months, which is why ancient watchers of the sky associated it with a swift messenger darting between the heavens. Its surface, when finally photographed in detail, turned out to look remarkably like our own moon, gray, cratered, and worn down by billions of years of impacts, a small, quiet world caught eternally close to the star that dominates its sky, burning on one side while ice waits patiently in the dark on the other. Mars keeps something like a memory written into its surface, the dry outlines of rivers and lake beds that have not carried water in a very long time. Orbiting spacecraft have mapped channels that wind and branch the way rivers do on Earth, complete with what look like deltas, the fan-shaped deposits left behind where a river once slowed and spread out before entering standing water. One crater, once considered a dry and unremarkable basin, is now believed to have held an ancient lake, its shoreline still faintly visible from above. This means Mars was not always the cold, thin, dusty world we see through telescopes today. Billions of years ago, it may have had a thicker atmosphere, a warmer climate, and enough liquid water flowing across its surface to carve these lasting scars into the rock. What changed remains one of the central mysteries of planetary science. The leading explanation involves the slow loss of Mars's magnetic field, which once may have shielded the planet's atmosphere from being stripped away by the solar wind. Without that shield, the atmosphere gradually thinned, the surface pressure dropped, and the water that once flowed openly either escaped into space or retreated underground and froze. Rovers exploring the surface today still find minerals that only form in the presence of liquid water, quiet chemical evidence tucked into ordinary-looking rock, hints of a wetter, gentler Mars, sitting patiently for us to notice. Far beyond Neptune, at the edge of what we still comfortably call our solar system, a small icy world named Pluto carries a bright, pale marking shaped almost exactly like a heart. It is a plain of frozen nitrogen, smoother than the cratered terrain around it, wide enough to stretch across a significant portion of the little planet's face. Beneath that frozen plain, scientists now suspect there may be a slushy ocean of liquid water, kept from freezing solid by heat left over from the planet's formation, and perhaps by antifreeze compounds mixed into the water below. Pluto also has mountains, some built not from rock as we would expect, but from water ice so cold and under such particular pressure that it behaves the way solid stone does here on Earth. Its largest moon, sharing an orbit locked so closely with its own that the two worlds essentially spin around a shared point of empty space between them, keeps one face permanently turned toward the other, forever. When a spacecraft finally passed close enough to photograph Pluto in detail, after a journey across the solar system lasting nearly a decade, it revealed a world far more active and complex than anyone expected from a small, icy body drifting so far from the sun's warmth. Glaciers of frozen nitrogen flow slowly across the heart-shaped plain, and the thin atmosphere, so faint it is barely there, still manages to form a delicate blue haze when sunlight passes through it at just the right angle. A quiet, cold beauty settled at the outer edge of everything we call home. Neptune is the most distant of the major planets, a deep blue world circling the sun so far out that sunlight there is little more than a dim twilight glow, and yet somehow it hosts the fastest winds ever measured on any planet in this solar system. Storms tear across its atmosphere at speeds far beyond anything found on Earth, fast enough that a hurricane here would seem gentle by comparison. For a while, Neptune displayed a storm known as the Great Dark Spot, a vast swirling system large enough to be seen from passing spacecraft. And then, within a handful of years, it simply vanished, dissolving back into the planet's deep blue haze before quietly reappearing somewhere else on the globe. Nobody fully understands why Neptune, sitting so far from the sun and receiving only a fraction of the warmth that reaches Earth, manages to produce weather this violent. Some scientists believe the planet's own internal heat, left over from its formation billions of years ago, plays a larger role in driving these storms than sunlight ever could. Neptune's brilliant blue color comes from methane in its upper atmosphere, which absorbs red light and reflects blue back toward any distant observer. Its single, large moon travels around the planet in the opposite direction to Neptune's own rotation, an orbit so unusual that many scientists believe the moon was not born alongside the planet at all, but was instead captured whole from somewhere else in the solar system's early, chaotic history. Deep inside Neptune and Uranus, far beneath the swirling methane clouds we can actually see, scientists believe it may rain diamonds. The idea sounds like something from fiction, but it follows directly from ordinary chemistry pushed to extraordinary pressure. Both ice giants contain large amounts of carbon in their deep atmospheres, and as you descend toward their cores, the pressure and heat climb to levels found almost nowhere else. Under those conditions, carbon atoms may be squeezed together into the same crystal structure found in the diamonds we know on Earth, forming small stones that then sink slowly downward through the layers of compressed gas and liquid below. Laboratory experiments here on Earth have attempted to recreate these deep planetary conditions, briefly compressing carbon compounds to enormous pressures and capturing evidence of tiny diamonds forming in an instant before the pressure is released again. If the theory holds, then somewhere inside Neptune, gentle showers of diamonds may be falling constantly, drifting down through thousands of kilometers of dense fluid before settling into a core we have never seen and likely never will. It is a strange thought that two of the coldest, most distant planets in our solar system might hold something we treasure so highly here on the surface of Earth, not as jewelry or ornament, but simply as an ordinary byproduct of pressure, buried far too deep for anyone to ever retrieve. Saturn's moon Titan is wrapped in a thick, hazy orange atmosphere, thicker even than the atmosphere surrounding Earth, and hidden beneath that haze lies something remarkable. Lakes and rivers, seas even, filled not with water but with liquid methane and ethane. Titan is the only place beyond Earth where we have directly observed standing liquid on the surface. Spacecraft images showing sunlight glinting faintly off the smooth surface of a distant polar sea. The temperature there sits so far below freezing that water exists only as rock-hard ice, forming the mountains and bedrock beneath Titan's strange hydrocarbon lakes. Rain falls there too, methane rain drifting down from thick orange clouds, filling river channels that wind across the surface almost exactly the way water carved the deltas of Mars long ago, just built from an entirely different chemistry. A probe once descended through Titan's atmosphere and landed gently on its surface, sending back images of a landscape strewn with what appeared to be rounded pebbles of ice, shaped by the slow, patient flow of liquid across them, much like stones smoothed by a riverbed on Earth. Some scientists wonder whether the ingredients for a very different, very alien kind of chemistry, perhaps even a very different kind of life, might exist in those cold hydrocarbon seas, chemistry built around methane instead of water, thriving quietly in conditions that would be lethal to anything we know, on a moon so far from the sun that its version of summer never grows warm at all. Europa, one of Jupiter's 4 large moons, looks from a distance like a smooth, cracked marble, its icy surface crisscrossed with long reddish lines that stretch for great distances across an otherwise pale white shell. Beneath that shell, most scientists now believe, lies a global ocean of liquid water, kept warm not by sunlight, which barely reaches this far into the solar system, but by the constant gravitational tug of Jupiter itself. As Europa orbits, the giant planet's gravity flexes and stretches the moon's interior, generating friction and heat deep inside, enough to keep an entire ocean liquid beneath a thick shell of solid ice. That ocean may hold more liquid water than every ocean on Earth combined, sealed away from sunlight and from the vacuum of space by a frozen crust that occasionally cracks and repairs itself, venting plumes of water vapor out into space through thin fissures in the ice. Scientists consider Europa one of the most promising places in this solar system to search for life beyond Earth, precisely because it has the 2 ingredients considered essential: liquid water and a source of steady internal energy, hidden away from the harsh radiation and cold of Jupiter's outer environment. Future missions are being designed specifically to fly close enough to sample those icy plumes directly, hoping to taste, in a sense, the chemistry of an ocean that has never once seen open sky. sealed beneath a moon that from the outside looks like nothing more than a quiet, cracked sphere of ice drifting around a much larger world. Io, another of Jupiter's large moons, could hardly be more different from its icy neighbor Europa. It is the most volcanically active body known anywhere in this solar system, its surface constantly reshaped by hundreds of active volcanoes spewing sulfur and molten rock high above the ground. The cause is the same gravitational flexing that warms Europa's hidden ocean. Except on Io, that same tidal stretching happens closer to Jupiter and with even greater intensity, generating so much internal friction that the moon's interior stays partially molten. Plumes of sulfur dioxide erupt from its surface and rise so high that some material escapes the moon entirely, forming a faint ring of particles that trails along Io's orbit around Jupiter. The surface itself is covered in yellows, oranges, and reds, colors created by sulfur compounds in different states, cooling and shifting across a landscape that looks almost nothing like anywhere else we have photographed. Lava lakes, larger than any found on Earth, sit exposed on the surface, glowing faintly, even in visible light images taken by passing spacecraft. Unlike most moons, which tend to be quiet, cratered, and largely unchanged for billions of years, Io resurfaces itself constantly, its old terrain buried under fresh eruptions again and again, meaning that whatever craters once existed there from ancient impacts have long since been paved over by molten rock rising from somewhere deep within this small, restless, endlessly active moon. Enceladus is a small, bright, icy moon of Saturn, and for a long time it seemed like a minor, unremarkable satellite until a passing spacecraft noticed something rising from cracks near its south pole. Plumes of ice and water vapor shooting outward into space with enough force to feed one of Saturn's fainter rings entirely on their own. That discovery revealed a hidden ocean of liquid water beneath Enceladus's icy shell, warmed once again by the gravitational tides of the much larger planet it orbits. Unlike Europa, where the ocean is sealed away and hard to reach, Enceladus offers its water directly to any spacecraft willing to fly through the plumes themselves, and one mission did exactly that, passing directly through the icy spray and detecting salts, organic molecules, and even hints of hydrogen, the kind of chemical ingredients associated with warm hydrothermal vents on the ocean floor of Earth. That combination excited scientists enormously, since it suggested Enceladus might have the chemistry needed to support simple microbial life somewhere in its dark, hidden sea. The surface above shows long parallel fractures near the pole, nicknamed tiger stripes for their banded appearance, warmer than the surrounding ice, and clearly the source of the venting plumes. Every time Enceladus completes another orbit around Saturn, it sprays a fine mist of its own ocean into space, some of which falls back as snow onto the moon itself, and some of which drifts outward to form Saturn's delicate outer ring, meaning that ring is, in a very real sense, made from the private, hidden ocean of a small moon, quietly sharing itself with the rest of the system. Between Mars and Jupiter lies a broad, scattered band of rock and rubble known as the asteroid belt, the leftover building material from the solar system's early history that never managed to gather itself into a full planet. Jupiter's immense gravity is largely to blame, tugging and disturbing the orbits of these small bodies so persistently that they were never allowed to settle together peacefully the way the planets did. Most of the objects in the belt are small, some no larger than a boulder, though a few grow large enough to be considered dwarf planets in their own right, round enough that their own gravity has pulled them into a sphere. Despite popular imagination showing crowded fields of tumbling rock, the asteroid belt is mostly empty space, so sparse that spacecraft have flown through it many times without needing to dodge anything at all. Some of these asteroids carry water ice and organic compounds locked inside their rocky interiors, materials thought to be similar to the raw ingredients that helped seed early Earth with the building blocks for life, delivered later by impacts. Studying them carefully offers a kind of time capsule, since many asteroids have remained largely unchanged since the solar system's earliest days, untouched by the volcanic activity and erosion that reshaped the surfaces of full-sized planets. Wandering silently between the rocky inner worlds and the gas giants beyond, this scattered belt of ancient debris holds quiet clues about how everything else in this solar system, including Earth itself, first began to take shape. Beyond Neptune stretches another, far larger band of icy bodies called the Kuiper Belt, a cold outer ring of debris left over from the solar system's formation, populated by small worlds of rock and ice that never grew large enough to be called full planets. Pluto is the most famous resident of this distant region, but it is far from alone. Another dwarf planet found out there, slightly more massive than Pluto itself, forced astronomers to reconsider what should and should not be called a planet at all, eventually leading to Pluto's own reclassification. The Kuiper Belt is thought to hold hundreds of thousands of icy bodies, remnants from a time when the solar system was still forming, pushed outward by the gravity of the giant planets rather than pulled inward to join them. Some of these distant bodies travel on strange, tilted, elongated orbits that carry them from the freezing edge of the Kuiper Belt to points even farther out, orbits so long that a single loop around the Sun can take centuries to complete. Because sunlight out there is so faint, barely more than a bright star in the sky, these objects remain frozen solid, locked in a kind of deep cosmic storage since the earliest days of the solar system. Every spacecraft that has ventured this far has needed years just to arrive, and years more before its signal, traveling at the speed of light, takes hours to reach Earth at all. Out here, at the true edge of what we still consider our neighborhood, the Sun becomes just another point of light, and the old rules of what counts as day and night begin to lose their meaning entirely. Jupiter's moon Ganymede holds a quiet distinction among every moon in this solar system. It is the largest one we know of, larger even than the planet Mercury, and it is the only moon ever found to generate its own magnetic field. That field wraps around Ganymede, the way Earth's own magnetic field wraps around our planet, deflecting charged particles and creating faint auroras near its poles, a moon behaving in some ways like a small planet in its own right. Beneath its icy crust, scientists believe there may be a layered structure of ice and liquid water, possibly holding more water than every ocean on Earth combined, sandwiched between layers of ice at different depths and pressures. Its surface shows two very different kinds of terrain: ancient dark regions scarred with countless craters, and brighter, younger regions crossed with long grooves and ridges, suggesting the moon's icy shell has shifted and cracked repeatedly over billions of years. Nearby, Jupiter's moon Callisto tells an even older story, its surface so heavily cratered that scientists consider it one of the most ancient, unchanged landscapes anywhere in the solar system, a moon that seems to have simply stopped evolving billions of years ago and quietly kept its scars ever since. Together, these two icy giants orbit alongside volcanic Io and ocean-covered Europa, four wildly different worlds circling the same planet, each shaped by its own particular distance from Jupiter's overwhelming gravity. A small and varied system of moons that in many ways resembles a miniature solar system all its own. Beyond our own solar system, thousands of other planets have been found circling distant stars, and almost none of them were seen directly. Instead, astronomers watch the light of a distant star for the faintest, briefest dimming, a tiny dip that repeats on a steady rhythm as a planet passes in front of its star from our point of view. The dip might only lower the star's brightness by a fraction of a percent, invisible to the eye but clearly measurable by a sensitive instrument watching patiently for years. From the timing and depth of that dimming, astronomers can work out a planet's size and how long its year lasts, sometimes even hints about the gases drifting in its atmosphere. It is a strange kind of discovery, finding an entire world not by seeing it, but by noticing the shadow it casts across the light of a star that may be hundreds of light years away. Space telescopes, built specifically for this purpose, have stared at the same patches of sky for years at a time, patiently logging the light of hundreds of thousands of stars, waiting for that rhythm to repeat. Thousands of confirmed worlds have emerged from this quiet, patient method, some of them rocky and small like Earth, others enormous and gaseous, orbiting so close to their stars that a single year passes in a matter of days. Every one of them began as nothing more than a flicker, a slight and steady dimming, noticed by someone willing to watch the same star long enough to see its secret. Some of the very first exoplanets ever confirmed turned out to be enormous gas giants, orbiting so close to their stars that a full year passes in only a few days, worlds now known as hot Jupiters. It seems strange at first, since nothing in our own solar system behaves this way. Massive gas giants like Jupiter and Saturn sit far out, well beyond the rocky inner planets, and yet here were planets of similar size sitting closer to their stars than Mercury sits to the Sun. The leading explanation is that these giants did not form in their current position at all, but instead formed farther out in colder regions of their systems, then slowly migrated inward over time, pulled by gravitational interactions with the disk of gas and dust they were born from. As they settled into their tight, fast orbits, the heat from their nearby star began to swell their outer atmospheres, sometimes stripping away material entirely, leaving faint, trailing streams of gas drifting behind the planet like the tail of a comet. Because they are so large and orbit so quickly, hot Jupiters were among the easiest kinds of exoplanets to detect early on, showing up again and again in the first searches. They remain some of the most extreme worlds cataloged so far. Planets built on the scale of Jupiter, but scorched by heat no gas giant in our own solar system will ever have to endure, drifting in tight, fast loops around suns that were never meant, by the old rules, to host anything this close. Some exoplanets may be covered almost entirely in water, with no land at all, no continents rising above the surface, just an endless global ocean stretching in every direction. These are sometimes called ocean worlds, and unlike the shallow seas of Earth, their water layers might extend for hundreds or even thousands of kilometers down before ever reaching solid rock. At that kind of depth, the pressure grows so extreme that water can no longer behave the way it does at the surface, compressing instead into strange, dense forms of ice that remain solid even while surrounded by warmth, simply because of the crushing weight above them. A planet like this might have a calm, gentle surface, mild winds, soft light reflecting off endless water, while far below, the physics of its interior grows steadily more alien with every passing stretch of depth. Some of these worlds may keep a rocky core buried deep beneath all that water and ice, warmed slightly by leftover heat from their formation. We have not yet confirmed a true ocean world beyond doubt, but the evidence keeps accumulating. Planets with just the right mass and just the right distance from their star to hold on to enormous quantities of water without losing it to space or freezing solid. If such worlds exist in the numbers scientists suspect, then oceans, rather than being a rare and precious feature of Earth, may turn out to be one of the more common outcomes when a planet forms with the right ingredients in the right place, a quiet abundance of water scattered further across the galaxy than we ever assumed. Some planets orbit so closely to their star that they stop spinning the way Earth does, and instead lock into place, with one side permanently facing the star and the other locked in permanent darkness. This happens gradually, over long stretches of time, as the star's gravity tugs at the planet's rotation until the spin slows to match the orbit exactly. The same effect that keeps our own moon showing only one face to Earth. On a planet locked this way, one hemisphere bakes under constant, unmoving daylight, while the opposite hemisphere never sees the star at all, existing in a permanent, frozen night. Between those two extremes runs a narrow band often called the twilight zone, a ring circling the planet where the star sits low and constant on the horizon, neither burning heat nor freezing cold, but somewhere gentler in between. Some scientists believe that if life were ever to take hold on a tidally locked planet, this quiet twilight strip might be the most likely place to find it, sheltered from the worst of both extremes. Winds on these worlds may behave strangely too, constantly flowing from the hot day side toward the cold night side, carrying warmth and moisture in one endless, unbroken current circling the globe. It is a strange way for a planet to live, permanently divided between light and dark, never once experiencing a sunrise or a sunset, only the fixed, unmoving edge of day, meeting night somewhere out along its horizon. Not every planet stays bound to a star for its entire existence. Some are flung outward during the chaotic early years of a planetary system, thrown loose by close encounters with other massive planets, until they escape their star's gravity completely and drift alone through the emptiness between stars. These are called rogue planets, wandering worlds with no sun to orbit, no daylight, no warmth beyond whatever heat they still hold onto from their own formation deep inside. They are extraordinarily difficult to find, since they give off almost no light of their own, but sensitive infrared instruments have managed to catch the faint residual glow of a few, drifting quietly through interstellar space. Some may still carry oceans hidden beneath thick shells of ice, kept liquid not by sunlight, which they no longer receive at all, but by the slow decay of radioactive material deep within their cores, the same kind of gentle internal heating that keeps Earth's own interior warm. Astronomers now suspect there could be a staggering number of these homeless worlds scattered throughout the galaxy, possibly even outnumbering the planets that still orbit stars. It is a quiet, lonely kind of existence, a planet moving endlessly through the dark, with no sunrise ever waiting for it, no seasons, no distant star warming its surface, just a slow, silent journey through the space between one star system and the next, carrying whatever warmth it managed to keep from the very beginning. Certain exoplanets may hold an unusual abundance of carbon rather than the oxygen-rich chemistry found on Earth. And under the right conditions deep within such a world, that carbon could be compressed into crystal form, the same structure found in a diamond. One promising candidate, a rocky planet roughly twice the size of Earth, is thought to have formed around a star with an unusually high ratio of carbon to oxygen, meaning its interior may contain vast quantities of compressed carbon, rather than the silicate rock that makes up most of Earth's crust. This would not look like anything sparkling or ornamental. There would be no polished facets catching starlight, just immense pressure, and deep below the surface, dense structures of pure carbon locked away in permanent darkness. Even the surface chemistry of such a planet might differ dramatically from our own, with graphite instead of soil, and an atmosphere carrying different gases entirely. It remains a theoretical picture more than a confirmed one, since no telescope can yet look directly inside a planet light years away. But the underlying chemistry checks out. Carbon behaves this way under pressure here on Earth, and there is no reason to think it would behave differently anywhere else in the galaxy. Somewhere out there, quietly orbiting a distant star, a planet may hold more diamond in its interior than has ever existed on the surface of our own, entirely unseen and entirely unreachable. Not every planet orbits just one star. In certain systems, two stars circle one another closely, locked together by gravity, and a planet can orbit both of them at once, tracing a wide loop around the pair, rather than settling around a single sun. These are known as circumbinary planets, and on such a world, the sky would show two suns rising and setting, sometimes together, sometimes at different times, depending on where the two stars happen to be in their own orbit around each other. Light on such a planet might shift constantly in color and intensity, brighter when both stars align on the same side of the sky, dimmer and more complex when they drift apart. Seasons on a world like this would follow no simple yearly pattern, shaped instead by the shifting relationship between two separate light sources rather than one steady star. A handful of these double sun systems have already been confirmed. Planets found circling pairs of stars that themselves complete a tight, fast orbit around each other every few days. It is a configuration once imagined only in fiction, distant worlds beneath a sky, holding two suns instead of one. And yet it turns out nature had already been quietly arranging exactly this kind of system long before anyone pictured it. Tucked away in corners of the galaxy, we only recently learned how to see. Most planets take months or years to complete a single orbit, but some exoplanets move so quickly around their star that an entire year passes in less than a single day here on Earth. These ultra-fast worlds sit unbelievably close to their stars. So close that their surfaces are likely molten, scorched by radiation and heat, far beyond anything a rocky planet in our own solar system ever experiences. One such planet, only slightly larger than Earth, completes a full lap around its star in under 9 hours, meaning that if you could somehow survive standing on its surface, you would watch an entire year pass before you finished a single ordinary workday. Gravity at such close range pulls at these planets constantly, and many are thought to be tidally locked, their day and night sides frozen permanently in place, even as the whole planet races around its star at tremendous speed. Some of these worlds may already be slowly disintegrating, their surface material gradually stripped away by the relentless heat and radiation pressing in from so close a distance. It is difficult to imagine time moving this quickly for an entire world, a planet living out its whole orbital year again and again within the span of what would be, for us, a single afternoon, spinning through blistering heat at a pace that makes the words day and year barely mean anything at all. Stars do not last forever, and when they reach the end of their long lives, some collapse into small, dense remnants called white dwarfs, while others explode and leave behind rapidly spinning cores known as neutron stars, some of which sweep beams of radiation around like a slow lighthouse as they turn. And, astonishingly, planets have been found orbiting both kinds of these stellar remains. The very first exoplanets ever confirmed were not found around an ordinary star at all, but around a spinning neutron star. Worlds circling a stellar corpse that no longer produces light through fusion, only a steady, rhythmic pulse as it spins. How planets could survive, or even form, around something that violent remains debated. Some may be survivors, worlds that endured the star's chaotic final years and simply kept orbiting afterward. Others may have formed later, built from leftover debris that settled into a disk around the collapsed star and slowly gathered together into new worlds. Around white dwarfs, astronomers have found similar evidence, faint traces of heavier elements drifting in the star's thin atmosphere, chemical signs suggesting that a planet, or the shattered remains of one, may still be orbiting nearby, slowly being pulled apart by the dead star's gravity. These are some of the strangest planetary environments we know of. worlds circling stars that no longer shine the way they once did. Quiet survivors, or perhaps quiet descendants, still tracing their orbits around the dim, cooling embers of a star that has already lived out its story. Saturn's rings remain one of the most recognizable sights in the entire solar system. A wide, thin disk of countless icy fragments circling the planet, some pieces no larger than a grain of sand, others as large as a house. From a distance they appear solid and smooth, but up close they are made of billions of individual particles, mostly water ice, each one following its own quiet orbit, nudged gently into place by the gravity of Saturn and its many moons. Scientists still debate exactly how these rings first formed, whether from a shattered moon torn apart by Saturn's gravity long ago, or from leftover material that never quite managed to gather itself into a moon in the first place. Some small moons orbit directly within gaps in the rings, their gravity carving clean lanes through the icy debris as they pass, shepherding the surrounding particles into narrow, well-defined bands. The rings are also surprisingly thin, spanning an enormous distance outward from the planet while remaining only a short distance thick, a vast, flat disk that would look almost like a sheet of paper if you could view Saturn from directly along its edge. Sunlight glinting off countless icy fragments gives the rings their pale, shimmering color, changing subtly with the seasons as Saturn slowly tilts toward and away from the Sun across its long orbit. It remains one of the gentlest, most beautiful structures in this solar system, a wide, quiet halo of ice, drifting endlessly around a planet far larger than anything nearby. Some exoplanets appear far larger than they should be for their measured weight, puffed up like balloons of gas rather than solid, dense worlds. These low-density planets, sometimes described as puffy giants, orbit close enough to their star that intense heat causes their outer atmospheres to swell dramatically, expanding the planet's visible size while barely adding to its actual mass. One such world is roughly twice the width of Jupiter, yet holds only a small fraction of Jupiter's weight, so light for its size that if you could somehow find an ocean large enough to hold it, the entire planet would float on the surface rather than sink. Radiation streaming from the nearby star may also be breaking apart molecules high in the atmosphere, adding to the strange, swollen quality of these worlds. Some show long, faint tails of escaping gas trailing behind them, slowly leaking away into space as the heat continues to strip material from their outer layers. They are not solid the way rocky planets are, nor as dense as most gas giants in our own solar system, but something softer, stretched thin by the relentless heat of a star sitting far too close. It is a reminder that a planet's size alone tells only part of the story, since two worlds of nearly the same width can carry wildly different amounts of actual matter, one dense and compact, the other little more than an inflated shell of gas, drifting gently around its star. Among the thousands of exoplanets discovered so far, a special category has drawn particular attention: worlds slightly larger than Earth but smaller than Neptune, often called super-Earths, some of which sit in just the right position around their star for temperatures that might allow liquid water to exist on the surface. One such planet, orbiting a small, dim star at a comfortable distance, receives roughly the same amount of light that Earth receives from the Sun, neither too much nor too little. Its larger size compared to Earth likely means stronger surface gravity, a thicker atmosphere, and possibly a more stable long-term climate, all factors that could make a world like this even more suited to hosting life than our own planet turned out to be. We cannot yet see the surface of these distant candidates in any real detail, so we do not know if they have oceans, continents, or clouds, only that their size, temperature, and orbit place them within a range worth watching closely. Some scientists believe planets like these could be common throughout the galaxy, quietly circling small, calm stars in numbers far greater than Earth, like planets around stars, similar to our own sun. It is a humbling thought that Earth may not represent the most comfortable possible version of a habitable world, simply the version we happen to know, while somewhere out there, a slightly larger, slightly calmer version may be circling its own star in patient, undisturbed silence. The clouds drifting through the atmospheres of certain hot exoplanets are not made of water vapor at all, but of vaporized minerals, the same materials that form solid rock here on Earth. On planets scorching hot enough for aluminum oxide or iron to exist as gas high in the atmosphere, that vapor can cool as it rises and condense back into tiny droplets, forming clouds built not from moisture, but from minerals normally found deep underground. In some cases, the mineral involved is the very same one that gives rubies and sapphires their color, meaning a planet's clouds might scatter light into deep reds, purples, or blues, depending on exactly which minerals are drifting through its upper atmosphere. Astronomers have picked up shifting patterns of brightness on a few of these worlds, subtle changes that suggest clouds moving and reshaping themselves the way clouds do on Earth, just built from an entirely different kind of material. It is difficult to picture a sky filled not with white and gray, but tinted faintly by clouds of drifting rock vapor, forming and dissolving under the relentless heat of a nearby star. These worlds remain far too hot and hostile for anything resembling life as we understand it. Yet the underlying beauty of the idea remains: a sky built from stone rather than water, glinting faintly in colors borrowed from gemstones, drifting silently above a surface no one will ever walk on. A small, quiet star, not much larger than Jupiter itself, turned out to host one of the most remarkable planetary systems ever found. 7 rocky worlds packed closely together, each roughly the size of Earth, orbiting so near one another that from the surface of one, a neighboring planet might appear larger in the sky than our own moon does from Earth. Because the star itself is so small and dim, all 7 planets orbit far closer than Mercury sits to our Sun, completing their years in a matter of days rather than months. And yet several of them still receive an amount of light gentle enough to sit within a plausible range for liquid water. The whole system moves with a kind of quiet precision, the orbits of the different planets locked into rhythmic ratios with one another. Gravitational relationships so stable they have likely persisted for billions of years without falling into chaos. Scientists have studied this system carefully, hoping to learn whether any of these worlds hold atmospheres thick enough to support water, or whether the star's flares have long since stripped them bare. It remains one of the most promising nearby systems for understanding what a compact family of rocky worlds circling a small, calm star might actually be, like up close, a tightly bound cluster of planets, moving together through the dark in careful, practiced harmony around a single, small, and steady source of light. Some of the planetary systems we have found are far older than our own, orbiting stars that formed when the universe itself was still young. One such system holds 5 small rocky planets circling a star more than twice the age of our Sun, meaning those worlds have been quietly completing their orbits for well over 10 billion years, longer than Earth has even existed. Because the early universe contained fewer heavy elements than it does now, planets that formed during that distant era may be built from a slightly different mix of materials than the rocky planets we know today. What such ancient worlds might look like up close remains a mystery, whether they carry deep scars from billions of years of impacts, or whether their surfaces have long since settled into something calm and unchanging. If life ever managed to take hold on a planet this old, it would have had an almost unimaginable stretch of time to develop, far longer than life on Earth has had so far. These ancient systems act almost like time capsules, quiet evidence that planets were already forming and settling into stable orbits not long after the first generations of stars began to shine. They remain bound to their stars today, circling steadily through the same rhythm they must have held for essentially the entire history of the universe, patient and unchanged, while everything else around them has transformed again and again. Not every star burns bright and fast. Many of the stars scattered across our galaxy are small, dim, and remarkably long-lived, cooler and calmer than our own sun, capable of shining gently for far longer than any star like ours ever could. Around some of these quiet stars, planets have been found sitting close enough to receive steady warmth without being blasted by the kind of dramatic flares that plague many other small stars. A planet orbiting a star like this might be tidally locked, one side forever facing the star while the other remains in permanent night, yet still hold a narrow, temperate band along its twilight edge where conditions could remain mild for an extraordinarily long stretch of time. Because these small stars burn their fuel so slowly, they are expected to keep shining steadily for far longer than our own sun ever will, meaning any planet fortunate enough to orbit one in calm, undisturbed conditions could have an enormous span of time for its environment to settle and, potentially, for life to develop and evolve. There is something quietly reassuring about a star like this, dim, patient, and steady, offering its planets not a brief flash of warmth, but an almost unimaginably long, slow, burning companionship, one that could continue for a length of time, far beyond anything our own solar system will ever experience. For most of the history of exoplanet science, every discovery came indirectly. A dimming of starlight, a subtle wobble in a star's position, never an actual picture of the planet itself. That began to change once telescopes grew precise enough to block out the overwhelming glare of a distant star and catch the much fainter light of a planet sitting nearby. The first such images were little more than faint, blurry points of light next to an artificially darkened star, but they were real, actual photons of light that had traveled from another planetary system directly into a telescope here on Earth. These early images captured enormous gas giants, still glowing faintly from the leftover heat of their own formation, orbiting slowly at a wide distance from their star. Watching several of these images taken years apart, astronomers could even see the faint point of light shift slightly in position, direct visual confirmation of a planet moving along its orbit, rather than simply inferred from starlight dimming or shifting. It marked a genuine turning point, the moment exoplanets stopped being purely a matter of mathematics and starlight patterns and became, however faintly, something we could actually see with our own instruments. Engineers continue refining new tools designed specifically to block starlight even more precisely, hoping eventually to capture clear enough images to study the atmospheres of smaller, rockier worlds directly, rather than only the largest and brightest gas giants drifting far from their stars. Once a telescope becomes precise enough, it can do more than simply detect a planet's presence. It can begin to study what that planet's atmosphere is actually made of. Using nothing more than starlight passing through the thin edge of the planet's air as it crosses in front of its star. As that light filters through the atmosphere, certain wavelengths are absorbed by specific gases, leaving a kind of fingerprint embedded in the starlight that eventually reaches our instruments. By carefully studying that fingerprint, scientists can identify signs of water vapor, carbon dioxide, methane, and other gases drifting in an atmosphere light years away. In a few promising cases, researchers have even begun searching for very specific chemical imbalances, Combinations of gases that are difficult to explain without some kind of biological process quietly maintaining them, often referred to as biosignatures. It remains careful, painstaking work, since clouds, temperature, and the type of star involved can all complicate the reading, and no single detection has yet offered clear, undisputed proof of life elsewhere. Still, each new spectrum gathered brings that possibility a little closer. An entire chemical portrait of a distant world's air, read quietly from starlight that took years, sometimes centuries, to finally arrive here, carrying whatever secrets that faraway atmosphere happened to hold. Jupiter carries the strongest magnetic field of any planet in this solar system, a vast, invisible bubble surrounding it that stretches far beyond the orbits of its own moons, so enormous that if it could somehow be seen from Earth with the naked eye, it would appear larger in the sky than the moon itself. That magnetic field traps charged particles streaming from the sun and from volcanic Io nearby, accelerating them until they collide with the planet's upper atmosphere near its poles, producing auroras far more powerful and far more constant than anything visible on Earth. Spacecraft passing near Jupiter's poles have photographed these auroras, glowing steadily in ultraviolet light, shifting and flickering as fresh particles pour in from the planet's own restless moon. The field is generated deep inside the planet, where immense pressure compresses hydrogen into a strange, dense, metallic form capable of conducting electricity the way liquid metal does, driving the powerful currents responsible for this enormous magnetic bubble. Any spacecraft venturing too close to Jupiter must be carefully shielded, since the radiation trapped inside that magnetic bubble is intense enough to damage delicate electronics within just a few passes. It is easy to imagine planets as simple spheres of rock or gas, quietly following their orbits. But Jupiter reminds us that a planet can also carry its own vast, invisible weather system built entirely out of magnetism and radiation, silently shielding and occasionally scorching everything that passes too close to its enormous, restless heart. Our entire solar system drifts through space, wrapped inside a vast, invisible bubble of its own, carved outward by the constant stream of particles flowing from the sun itself, known as the solar wind. That bubble, sometimes called the heliosphere, extends far beyond the orbits of every planet, pushing back against the thin gas and dust that fills the space between stars, creating a kind of gentle boundary between our own neighborhood and the rest of the galaxy. Only a small handful of spacecraft have ever traveled far enough to cross that boundary and measure conditions on the other side, sending back readings that showed a sudden, clear shift once they finally passed beyond the edge of the sun's influence entirely. Inside this bubble, our solar system enjoys a certain amount of quiet shelter, some protection from the harsher radiation drifting through interstellar space beyond it. Some scientists believe the size and shape of this bubble shifts slowly over long stretches of time, expanding and contracting gently as the sun's own activity rises and falls across its slow, ongoing cycles. It is a strange thought that everything we know, every planet, every moon, this entire solar system, sits nested quietly inside a slow-moving bubble of solar wind, drifting together through the wider galaxy, carried along as one single, sheltered pocket of space. Far beyond even the Kuiper Belt, at the outermost edge of the sun's influence, astronomers believe there exists a vast, distant shell of icy material called the Oort cloud, a sphere of countless small frozen bodies surrounding the entire solar system at a distance so great that sunlight there would be barely brighter than any other star in the sky. No spacecraft has ever traveled far enough to reach it directly, and every part of its existence has been inferred rather than seen, mostly from the long, slow orbits of certain comets that swing in toward the sun only once every few thousand years before disappearing back out into the darkness. These distant icy bodies are thought to be leftover material from the solar system's earliest days, nudged outward long ago by the gravity of the giant planets, and now drifting in a slow, wide shell that may extend nearly halfway to the nearest neighboring star. Occasionally, the gentle gravitational pull of a passing star, even one located an enormous distance away, can nudge one of these icy bodies loose, sending it falling slowly inward across thousands of years until it eventually becomes visible from Earth as a bright comet with a long, glowing tail. It is humbling to consider that our solar system does not end cleanly at Neptune or even at the Kuiper Belt, but instead fades gradually outward into this enormous, sparse cloud of ancient ice. A quiet, frozen boundary between our own small neighborhood and the vast emptiness that separates every star from the next. Comets themselves are often described as dirty snowballs, loose mixtures of ice, dust, and frozen gases that spend most of their existence in the cold outer reaches of the solar system, only becoming active once their long orbit finally carries them close enough to the sun to feel real warmth. As the ice begins to vaporize, it releases gas and dust that stream outward from the comet's small icy core, forming a temporary atmosphere and a long, glowing tail that always points away from the sun, regardless of which direction the comet itself happens to be traveling. Some comets return on a predictable schedule, swinging past Earth once every few decades, while others arrive only once in a human lifetime, or once in many lifetimes, before vanishing back out toward the Oort cloud for another long, cold journey lasting thousands of years. Each pass near the sun costs a comet a small portion of its material, meaning that with enough repeated visits, some eventually burn away entirely, leaving nothing behind but a faint trail of dust scattered along their old path. It is a strange kind of life for an object to lead, spending nearly its entire existence frozen and dark, far from any star, only occasionally waking briefly into a glowing, active visitor before slipping back into the cold and the dark for another few thousand years of silence. Auroras are not unique to Earth, and in fact, some of the most spectacular light shows in this solar system happen on other planets entirely. Saturn's poles glow with faint ultraviolet auroras, driven by the same kind of charged particle activity that lights up the sky above Earth's own polar regions. Though shaped by a magnetic field very different from our own. Even distant Uranus and Neptune, tilted and strange as they are, have shown faint auroral glows near their poles, evidence that their own magnetic fields, oddly shaped and offset from the planet's center in ways scientists still do not fully understand, still manage to funnel charged particles down into their thin outer atmospheres. On Jupiter, the auroras are driven partly by particles from the sun, but largely by material erupting from volcanic Io, creating a constant, glowing footprint at the planet's poles that never fully fades the way Earth's auroras do. Each planet's auroras carry the fingerprint of its own particular magnetic field, its own atmosphere, and its own nearby sources of charged particles, meaning no two planets in this solar system light up their skies in quite the same way. It is a quiet reminder that the shimmering curtains of light we sometimes see dancing above Earth's own poles are not some rare accident belonging only to us, but simply one version of a phenomenon playing out in its own unique way, above nearly every planet, with a magnetic field strong enough to catch and funnel the endless stream of particles drifting through this solar system. Every planet we have ever studied, whether inside our own solar system or orbiting some distant star hundreds of light years away, was built from the same basic ingredients: the leftover dust and gas surrounding a newly formed star, gradually gathering together under the patient, steady pull of gravity. And yet the sheer variety among the results remains staggering. Small planets and enormous ones, scorching worlds and frozen ones, planets locked forever between light and dark, planets circling two suns at once, planets drifting entirely alone with no star at all. Every new discovery adds another version of what a planet can become. Another reminder that the same simple process of dust slowly gathering into rock, or gas slowly gathering into atmosphere, can produce results as different from one another as anything we could imagine. Current estimates suggest there may be more planets scattered throughout our galaxy than there are stars. Hundreds of billions of worlds, most of which will never be studied closely, most of which will remain nothing more than a distant flicker of dimmed starlight to anyone watching from here. It is a strange kind of quiet abundance, an entire galaxy filled with worlds we will mostly never see in any detail, each one turning patiently through its own version of day and night, warmth and cold, light and dark, far beyond anything we will ever be able to visit ourselves. Ceres sits quietly within the asteroid belt between Mars and Jupiter, the largest object out there by a wide margin, round enough that its own gravity has pulled it into a proper sphere, which is part of why it earned the designation of a dwarf planet rather than simply another chunk of rubble. For a long time it seemed like a plain, unremarkable body, until a spacecraft arrived close enough to notice strange, bright spots scattered across the floor of one of its craters, patches so reflective they seemed almost out of place against the otherwise dark, dusty surface. Those spots turned out to be deposits of salt, left behind after briny liquid seeped up from below and evaporated, evidence of a slushy layer of water and minerals still shifting somewhere beneath Ceres's crust. That discovery reframed the entire little world, suggesting it might still hold on to small pockets of liquid, or at least very recently active geology, hidden beneath a surface that appears cold, gray, and unchanging from a distance. There is even a tall, isolated mountain rising from an otherwise flat plain, believed by some scientists to be the remains of an ancient cryovolcano, a mountain built not from molten rock, but from icy material that once oozed slowly upward before freezing solid in place. Ceres reminds us that even the smaller, quieter bodies scattered through this solar system, easily overlooked in favor of the larger planets nearby, can still carry hidden chemistry and slow, ongoing activity beneath a surface that looks, from any distance, perfectly still. Neptune's largest moon, Triton, does not orbit the way most large moons do, circling its planet backwards, in the opposite direction to Neptune's own rotation. A strong clue that Triton was never actually born alongside Neptune at all, but was instead captured whole sometime in the ancient past, likely a wandering icy world, originally from the outer edges of the solar system, that drifted too close and was pulled permanently into orbit. That backwards orbit is slowly, gradually shrinking Triton's distance from Neptune, and many scientists believe that many millions of years from now, the moon will eventually drift close enough to be torn apart entirely by Neptune's gravity, potentially forming a new ring system in its place. For now, Triton remains remarkably active for such a distant, frozen moon, with geysers of nitrogen gas and dark dust erupting from beneath its icy surface, rising into its thin atmosphere before drifting downwind and settling back down as dark streaks visible across the pale ice. Its surface temperature ranks among the coldest ever measured on any body in the solar system, and yet somehow, deep beneath that frozen crust, enough heat remains to drive these strange, cold volcanic eruptions of gas rather than molten rock. A single spacecraft passed by Triton only once, decades ago, capturing a brief glimpse of a moon unlike almost anything else nearby, an icy, backwards, orbiting captive, slowly spiraling closer to the very planet that once reached out and claimed it. Somewhere between the size of a large planet and a true star sits a strange category of object called a brown dwarf. Massive enough to briefly ignite a limited kind of nuclear fusion early in its life, but never quite massive enough to sustain the kind of steady fusion that keeps ordinary stars shining for billions of years. Instead, a brown dwarf simply glows faintly with leftover heat from its own formation, gradually cooling and dimming over enormous stretches of time, neither a planet in the usual sense, nor a star in any meaningful one. Some brown dwarfs drift entirely alone through space, never orbiting anything, while others circle a proper star at a wide distance, quietly blurring the boundary between what should be called a planet and what should be called a failed star. Scientists still debate exactly where that boundary lies. Since some brown dwarfs are barely more massive than the largest confirmed planets, while others sit much closer to the lower mass limit required for a true star to ignite. Because they emit so little visible light, brown dwarfs are usually detected using infrared instruments, sensitive enough to catch the dim residual warmth radiating from an object that never fully earned its place among the stars. They exist in a strange, patient category of their own, too big to be ordinary planets, too small to ever burn the way real stars do, drifting through the galaxy in the quiet, dim in between. Just as planets orbit stars, it stands to reason that many planets beyond our own solar system should have moons of their own. And astronomers have spent years searching carefully for the first confirmed example of one, an exomoon circling a distant exoplanet. The search is difficult, since a moon's effect on the light of a distant star is even fainter and harder to detect than the planet's own signal, a subtle secondary dimming or timing shift buried within data that is already close to the very edge of what our instruments can measure. One promising candidate, a moon potentially large enough to rival some planets in our own solar system, orbits a distant gas giant and has kept astronomers cautiously intrigued for years, though the data remains difficult to confirm completely. If large gas giants elsewhere in the galaxy behave anything like Jupiter and Saturn do here, each one hosting dozens of moons of wildly different sizes and compositions, then exomoons are likely common throughout the galaxy, simply waiting for our instruments to grow sensitive enough to catch them clearly. Some of these unseen moons could even sit within a comfortable temperature range of their own, warmed gently by their planet's heat as well as by their star, holding on to oceans hidden beneath icy shells, much like several moons already found much closer to home. For now, they remain mostly theoretical, quiet possibilities tucked just beyond the edge of what current instruments can prove, waiting patiently for the day telescopes finally grow sharp enough to notice them directly. Around every star there exists a narrow, gentle band of distance, close enough that a planet does not freeze solid, far enough that it does not scorch and boil away, a comfortable middle ground, often called the habitable zone. Earth sits comfortably within our own sun's version of this zone, close enough to keep its oceans liquid, far enough to avoid the fate of scorched, cloud-choked Venus just one orbit closer in. But the boundaries of this zone are rarely as simple as distance alone. A planet's atmosphere plays an enormous role too, since a thick blanket of greenhouse gases can keep a distant, dim world warm enough for liquid water, while a thin, fragile atmosphere might leave an otherwise well-positioned planet cold and frozen despite receiving plenty of light. Around smaller, cooler stars, the habitable zone sits much closer in, tight and narrow, while around larger, brighter stars it spreads out much farther, sometimes reaching several times the distance Earth sits from our own sun. Astronomers use this concept as a starting point, a rough filter to help decide which of the thousands of confirmed exoplanets deserve the closest attention when searching for worlds that might resemble our own. Being inside this gentle zone is no guarantee of habitability by itself, only an invitation, a hint that conditions might be right if everything else about that distant world happens to line up as gently and as fortunately as it did once here at home. Earth carries two quiet, invisible forms of protection that many other planets simply do not have. A strong magnetic field generated deep within its molten core, and a thick, stable atmosphere held firmly in place by that same field, working alongside the planet's gravity. Together, they shield the surface from much of the harsh radiation and charged particles streaming constantly outward from the sun, deflecting the worst of it harmlessly around the planet rather than letting it strip away the atmosphere the way it appears to have happened on Mars billions of years ago. Without that magnetic shield, scientists believe Earth's own atmosphere might have slowly bled away into space over time, leaving behind a thinner, colder, far less hospitable world, much like the dry red planet we see today. It is easy to take this kind of quiet protection for granted, since it produces no dramatic events, no violent storms, nothing visible at all beyond the occasional soft glow of an aurora near the poles. And yet it may be one of the single most important reasons life managed to take hold here and continue for as long as it has. Many of the exoplanets we study most closely are judged not only by their distance from their star, but by whether they are likely to carry a magnetic field strong enough to offer this same kind of quiet, invisible shelter, a factor just as important, in its own understated way, as temperature or the simple presence of water. Far beyond the orbit of Neptune, in the coldest, darkest reaches of the solar system, some astronomers believe there may be an enormous, undiscovered planet quietly circling the Sun on an orbit so wide that a single loop could take many thousands of years to complete. The evidence for this hidden world does not come from any direct image, but from the strange, clustered orbits of several small, distant icy bodies far out past the Kuiper Belt. Orbits that seem to align in a way best explained by the gravitational influence of something large and unseen nearby. If it exists, this hypothetical planet could be several times the mass of Earth, sitting so far from the Sun that its own version of daylight would be little more than a faint, distant point of light, dimmer than any sunset ever seen from Earth. Searching for it has proven extraordinarily difficult, since an object this cold and this far away reflects almost no light at all, and the region of sky it might occupy is enormous, far larger than any single survey can easily cover. Some scientists remain skeptical, suggesting the strange orbital clustering might be explained by other means entirely, perhaps simply the way the solar system's edge naturally settled over billions of years. Still, the search continues quietly in the background of modern astronomy, telescopes occasionally turning toward the faint, frozen edge of our own solar system, hoping to finally catch a glimpse of a planet that, if it is really there, has been circling patiently in the dark long before anyone ever thought to look for it. Earth's own moon, likely formed from violence rather than anything gentle. The leading explanation describing a collision early in the solar system's history between the young Earth and another planet-sized body, roughly the size of Mars. That impact would have thrown an enormous amount of molten debris into orbit around Earth, material that gradually cooled, gathered together under its own gravity, and eventually formed the moon we see today. It is a strange thought that the quiet, familiar object hanging in our night sky, the same moon that has guided tides and calendars for the entire span of human history, began as scattered debris flung outward from a catastrophic collision between two young worlds. Evidence for this violent origin comes partly from the strong chemical similarities between rocks brought back from the lunar surface and rocks found here on Earth. Similarities that would be difficult to explain if the moon had simply formed independently elsewhere and been captured later. The moon has also been slowly drifting farther away from Earth ever since, moving outward by a small amount every year, meaning it was once far closer, hanging much larger and brighter in the ancient sky than it does tonight. Long before written history, before language, before anything resembling civilization, that same moon was already there, freshly formed from violence, slowly settling into the quiet, steady companion it has remained ever since. Not every asteroid is a simple, uniform lump of rock. Vesta, one of the largest bodies in the asteroid belt, turned out to be layered on the inside much like a true planet, with a dense metallic core, a rocky mantle surrounding it, and a thin outer crust, a structure that only forms when a body grows large enough and hot enough early in its history for heavier material to sink toward the center, while lighter material rises to the surface. This process, called differentiation, is the same one that shaped Earth's own layered interior, which makes Vesta something like a small, frozen fossil of planetary formation, a body that started down the same path as a full-sized planet before running out of material to keep growing. A massive ancient impact once carved an enormous crater near Vesta's south pole, so large relative to the asteroid's own size that the collision very nearly shattered the entire body apart, leaving behind a mountain at the center of the crater taller than almost any mountain found on Earth. Fragments blasted loose by that same impact eventually made their way to Earth as meteorites, meaning some of the very same material sitting on the shelves of certain laboratories arrived here after a journey lasting millions of years from the asteroid belt. Vesta remains one of the clearest surviving examples of what a planet looks like partway through its own formation. Frozen at an early stage, a small layered world that never quite finished becoming anything larger, drifting quietly among the other rubble of the asteroid belt. Look closely at the color of any planet in this solar system, and you are really looking at the particular chemistry of its outer atmosphere. Jupiter and Saturn both glow in warm bands of tan, cream, and pale orange, colors created by ammonia, clouds, and various compounds swept into stripes by each planet's own powerful rotation and internal heat. Uranus and Neptune, farther out and much colder, take on a cooler blue and blue-green tone instead, caused by methane gas high in their atmospheres, which absorbs red light and reflects blue back toward any telescope watching from Earth. Mars earns its familiar reddish tint from iron oxide, essentially rust, coating fine dust that covers much of its dry, rocky surface. Venus, wrapped permanently in thick, reflective clouds of sulfuric acid, appears pale and featureless from a distance, hiding its scorched surface entirely beneath an unbroken layer of pale yellow-white haze. Even small, icy worlds far out past Neptune show subtle color variation, some pale and white, others tinted faintly reddish by ancient organic compounds exposed to billions of years of radiation. None of these colors are painted on or arbitrary. Each one is a direct clue about the chemistry drifting through that planet's atmosphere, meaning the simple color of a distant world glimpsed through even a modest telescope is really a small, quiet chemistry lesson written in light. Saturn's small, icy moon Mimas carries a single, enormous crater on one side, so large, relative to the moon's overall size, that the entire object bears an unmistakable resemblance to a certain fictional space station, wide enough to stretch across a significant fraction of the moon's diameter, with a central peak rising from its floor nearly as tall as the crater is deep. Whatever object struck Mimas long ago came remarkably close to shattering the small moon apart entirely, and cracks running along the opposite side of the moon suggest the shock of that ancient impact traveled all the way through the icy body and back out again. Despite carrying a scar this dramatic, Mimas remains a small, quiet moon, tidally locked to Saturn, orbiting patiently within the outer regions of the planet's magnificent ring system. More recent observations have hinted that Mimas may hold a young, recently formed ocean of liquid water sealed beneath its icy shell. A surprising possibility for a moon so small and so heavily cratered that scientists long assumed it was simply frozen solid all the way through. If that hidden ocean is real, it would place Mimas alongside its more famous neighbor Enceladus as another small, icy world, quietly hiding liquid water beneath a cold, scarred surface. A moon that looks, from any passing spacecraft, like nothing more than a battered ball of ice, while potentially holding something far more interesting, hidden away just beneath that ancient impact scar. Uranus carries its own faint system of rings, discovered almost by accident when astronomers watched the planet pass in front of a distant star, and noticed the star's light flicker and dim several times before Uranus itself even reached it. Evidence of thin, dark material orbiting the planet that no one had previously detected. Unlike Saturn's wide, bright, icy rings, Uranus's rings are narrow, dark, and made largely of material that reflects very little light, which is likely why they remained hidden for so long, even from careful observation. Small shepherd moons orbit closely alongside these narrow rings, their gravity helping keep the material confined into tight, well-defined bands rather than spreading out and dispersing over time. Because Uranus itself lies tipped almost completely on its side, its rings appear to circle the planet vertically from our point of view here on Earth, rather than the familiar flat, wide halo we associate with Saturn. Very little sunlight reaches this distant, tilted world in the first place, meaning these dark, narrow rings drift in an environment of near constant dim twilight, circling a sideways planet that itself spends decades at a time locked into either endless daylight or endless night, depending on the season. It remains one of the quieter, lesser-known ring systems in the solar system, easy to overlook next to Saturn's famous bands. Yet another small reminder that rings, once thought to be a rare feature belonging only to one particular planet, may actually be a far more common structure than anyone originally assumed. Somewhere out in the asteroid belt drifts an object unlike almost anything else nearby. An asteroid believed to be made largely of metal rather than rock, possibly the exposed core of a much larger body that lost its outer rocky layers long ago in some ancient collision. Scientists, studying it from a distance, have found signs of iron and nickel dominating its composition, materials similar to what makes up Earth's own deep metallic core. Hidden here, on the surface of the asteroid, where any spacecraft could eventually study it directly. If the leading theory holds, this metal-rich body may once have been part of a planet in the process of forming, one that grew large enough for heavier metal to sink toward its center the way it did on Earth, before a violent impact stripped away its outer rock and left only the dense metallic heart behind, drifting alone through the belt ever since. Studying an object like this offers something no drill or borehole on Earth could ever provide: a direct look at the kind of material that likely fills the deep interior of every rocky planet, without needing to dig through thousands of kilometers of rock to reach it. A mission has already been sent to study this strange metallic world up close, hoping to confirm exactly how much of it truly is iron and nickel, and what its surface might reveal about the violent, unfinished history of a planet that never got the chance to fully form. Far beyond even the distant Kuiper Belt drifts a small, reddish world on one of the longest and most stretched orbits ever measured for any object in the solar system. Swinging in toward the sun only briefly before spending centuries drifting back out into a stretch of space, so remote that sunlight barely registers there at all. Its orbit is so elongated that even at its closest approach, it remains farther from the sun than nearly everything else we have ever closely studied. And at its farthest point, it travels into a region so isolated that some scientists consider it a bridge between our own solar system and the distant, icy Oort cloud beyond. Nobody is entirely sure what nudged this small world onto such an extreme, elongated path. Though some propose a passing star long ago may have tugged it outward, while others wonder whether an undiscovered planet drifting somewhere in the outer solar system might be responsible. Its reddish surface color suggests ancient organic material, similar to what has been found on other small, icy bodies drifting at the edge of the solar system. Chemistry that has likely remained almost entirely unchanged since the solar system's earliest days, simply because so little sunlight or warmth ever reaches it. It completes a single orbit only once every several thousand years, meaning that since it was first discovered, it has barely begun the long, slow return trip back toward the distant outer darkness. It spends nearly its entire existence drifting through. Pluto's thin atmosphere behaves in a way unlike anything found on the larger planets closer to the Sun, expanding and thickening slightly as Pluto's long, elongated orbit carries it closer to the Sun, then slowly collapsing back down onto the surface as frost once Pluto drifts farther away again into the cold outer reaches of its own orbit. During its warmer stretch, sunlight causes a portion of Pluto's frozen nitrogen surface to turn directly into gas, briefly thickening the atmosphere, enough for spacecraft instruments to detect a faint, delicate haze layered above the surface. As Pluto swings back outward on its long, slow path, temperatures drop enough that this same nitrogen gas begins to fall back down and refreeze, essentially causing Pluto's atmosphere to rise and fall gently in step with its own orbit, rather than with any daily or yearly rhythm familiar to us on Earth. Nearby, Pluto's large moon Charon orbits so closely, and the two bodies are so evenly matched in relative size, that they do not simply orbit one another the way a planet and a smaller moon typically do, but instead both circle a shared point of empty space between them, each one permanently facing the other, forever locked together in a slow, silent, mutual orbit. From Pluto's surface, Charon would never rise or set at all, hanging motionless in exactly the same spot in the sky day after day, a companion moon that never moves, watching over a small, distant world where the very atmosphere itself breathes slowly in and out across each impossibly long and distant year. Jupiter shares its orbit around the Sun with two large clusters of asteroids, trapped gently in the same orbital path as the giant planet itself, one cluster trailing behind Jupiter and one following ahead of it, held in place by a delicate gravitational balance between the Sun and Jupiter's own enormous mass. These are known as Trojan asteroids, and thousands of them have been discovered so far, ranging from small fragments to bodies large enough to be considered minor worlds in their own right. They neither drift closer to the Sun nor spiral outward away from Jupiter, held instead in a kind of quiet gravitational parking spot that has likely remained stable for billions of years since the early days of the solar system. Even Earth carries a single known companion of its own kind, a small asteroid trapped in a similar gentle balance point along our own orbit, quietly following the same path around the Sun that Earth itself takes every single year without ever coming particularly close. These trapped companions are thought to be leftover material from the solar system's earliest formation, captured into these stable positions before they ever had the chance to either fall inward toward the sun or scatter outward into deep space. It is a quiet, easily overlooked detail of this solar system that alongside every planet's own steady orbit, small companions may be riding along in the same gravitational lane, drifting patiently just ahead or just behind, invisible to the naked eye, but held firmly in place all the same. Some exoplanets grow to sizes far beyond anything found in our own solar system. Gas giants many times more massive than Jupiter, sitting right at the edge of what can still be called a planet rather than a small, failed star. These enormous worlds often orbit far from their star, glowing faintly with heat left over from their own formation, rather than from any sunlight reaching them from so great a distance. Their gravity would be immense, strong enough that any moon orbiting closely might itself grow large enough to hold on to a thick atmosphere of its own, essentially becoming a small world in its own right, shaped and warmed by the enormous planet it circles rather than by the star far beyond. Weather systems on a planet this size could span entire hemispheres, storms larger than anything Jupiter has ever produced, swirling for centuries at a time across an atmosphere far deeper and far more massive than our own solar system's largest gas giant. Scientists continue debating exactly where the line should be drawn between a very large planet and a very small brown dwarf, since some of these massive worlds sit almost perfectly at that blurry boundary, more massive than anything comfortably called a planet, yet still short of whatever threshold allows even brief nuclear fusion to begin. They remain some of the most extreme worlds cataloged so far, quiet giants drifting at the outer edges of their own systems, too small to shine, too large to be considered ordinary, holding their own private, oversized version of what a planet can become. Beyond Pluto, in the same distant, icy region of the solar system, another small, reddish dwarf planet drifts on a long, tilted orbit of its own, discovered only recently and immediately notable for spinning remarkably fast for a body its size, completing a full rotation in only a handful of hours rather than the longer days typical of most planets and dwarf planets nearby. That rapid spin appears to have stretched the little world slightly, giving it an elongated, football-like shape rather than the more rounded forms seen on most other icy bodies out at the edge of the solar system. It even carries two small moons of its own, tiny icy companions caught in orbit around a dwarf planet that itself is smaller than our own moon, a miniature system of worlds circling one another far out in the cold and the dark. Its surface appears unusually bright and icy compared to many of its neighbors, suggesting a layer of crystalline water ice coating the exterior, distinct from the duller, redder material found on many other distant bodies drifting through the same region. Objects like this one continue to reshape our understanding of just how varied and unexpected the far outer solar system can be. Small icy worlds spinning quickly, shaped strangely, carrying their own tiny moons, drifting quietly through a region we only began exploring in any real detail within living memory. Mars keeps company with two small, oddly shaped moons, Phobos and Deimos, each one far too small and irregular to have ever pulled itself into a proper sphere, more closely resembling a lumpy, cratered potato than the round moons we usually picture. Both are widely believed to be captured asteroids, drifting too close to Mars sometime in the distant past and becoming permanently trapped by its gravity, rather than forming alongside the planet the way our own moon likely formed alongside Earth. Phobos, the larger and closer of the two, orbits so near to Mars that it circles the planet faster than Mars itself rotates, meaning that from the surface, Phobos would appear to rise in the west and set in the east, crossing the sky several times within a single Martian day. That same closeness is slowly working against it, since Mars's gravity is gradually pulling Phobos inward, tightening its orbit a small amount with every pass. A slow spiral that scientists expect will eventually end with the little moon either crashing into the surface or being torn apart entirely, potentially forming a temporary ring around Mars in the process. Deimos, smaller and more distant, drifts on a calmer, more stable orbit, taking considerably longer to circle the planet and facing a far less dramatic future. Together, these two small, quiet companions circle a planet that itself once may have hosted flowing rivers and standing lakes, two humble, irregular little worlds keeping watch, in their own slow orbits, over the dry, red landscape below. Venus rotates on its own axis remarkably slowly, so slowly that a single day there stretches longer than its own year, and yet high above the surface, the thick atmosphere itself races around the entire planet in only a few days, a phenomenon scientists call superrotation, where the winds move dramatically faster than the ground beneath them ever does. Nobody has fully settled on why this happens, though it likely involves a complex exchange of energy between solar heating and the thick, churning layers of sulfuric acid clouds that permanently blanket the planet. This means that while the solid surface of Venus turns at an almost imperceptible crawl, the clouds above sweep around the entire globe again and again within the time it takes Earth to complete just a single week. An entire planet's worth of weather circling far faster than the world underneath it ever moves. Spacecraft studying Venus from orbit have tracked these fast-moving cloud patterns for years, watching bands of haze and streaks of lighter and darker cloud drift steadily around the planet at speeds that seem almost mismatched with how sluggishly Venus itself turns. It remains one of the more puzzling mysteries of our neighboring planet, a surface locked into an almost motionless rotation, wrapped underneath an atmosphere behaving as though it belongs to an entirely different, far faster spinning world. Deep inside Uranus and Neptune, far below the pale, hazy clouds visible from space, scientists suspect conditions grow strange enough that ordinary water stops behaving like the liquid or ice we know it all. Under the immense pressure and heat found in that deep interior, water, ammonia, and methane may combine into a thick, slushy layer, sometimes called an ice mantle, even though it likely behaves more like a hot, dense, electrically conductive fluid than anything resembling solid ice on the surface. Some laboratory experiments have even recreated similar pressures briefly, suggesting that under these extreme conditions, water can enter an unusual state, sometimes called superionic, where oxygen atoms remain fixed in a solid lattice, while hydrogen atoms flow freely through it, behaving almost like a liquid and a solid at the same time. This strange layer is thought to be responsible for the unusual and lopsided magnetic fields of both Uranus and Neptune, fields that, unlike Earth's own tidy, centered magnetic field, appear tilted and offset from the very center of each planet. Nobody has ever sampled this interior layer directly, and likely never will, given the crushing pressures and immense depth involved. So, everything we understand about it comes from careful modeling and small-scale laboratory experiments, attempting to recreate just a sliver of those extreme conditions. It remains one of the more exotic hidden layers in this entire solar system, a thick, strange, electrically active ocean sealed away far beneath the calm blue haze that is the only part of either ice giant we have ever actually seen. Rings, once considered a feature belonging almost exclusively to the large gas giants of the outer solar system, turned out to exist in far smaller and stranger places too. A small icy body called Chariklo, drifting in the outer solar system between the orbits of Saturn and Uranus, was found to carry two thin, narrow rings of its own, the first rings ever discovered around an object this small, far tinier than any full-sized planet. Astronomers noticed them the same way Uranus's own rings were first detected, by watching the small body pass in front of a distant star and noticing brief, unexpected dips in the star's light, both before and after the main object itself blocked it. Nobody expected an object this size to hold on to rings at all, since such a small amount of gravity would typically struggle to keep orbiting material confined into narrow, stable bands, rather than letting it drift apart or collapse into a small moon over time. The discovery reshaped assumptions about what kind of object can host a ring system, suggesting that rings may be a far more common structure throughout the solar system than anyone previously imagined. Simply too faint and too small to have been noticed around smaller bodies until instruments grew precise enough to catch the fleeting shadow they cast while passing in front of a star. It has only been a few decades since the very first planet orbiting another sun like ours was confirmed beyond any doubt, a discovery that at the time reshaped an entire field of study almost overnight. Before that moment, every planet we knew of belonged to our own solar system, a small, familiar family of 8 worlds circling one particular star. Since then, the pace of discovery has only accelerated, moving from a single confirmed exoplanet to many thousands, each one adding another data point to our slowly growing picture of what planets throughout the galaxy actually tend to look like. Space telescopes built specifically for this kind of patient, long-term search have stared at the same small patches of sky for years at a stretch, quietly logging the subtle rhythm of starlight, dimming again and again until a pattern could be confirmed. Newer instruments continue refining that search even further, capable now of studying not just whether a planet exists, but increasingly, what kind of atmosphere it might carry, what gases might drift through its skies, what kind of world it might actually be up close. It is worth remembering, in the middle of everything we have covered tonight, that essentially all of this understanding has arrived within a single human lifetime, an entire new branch of astronomy built almost from nothing within the span of a few short decades, and one that continues expanding with every year that passes. Standing back from every individual world we have wandered through tonight, from scorching planets locked eternally toward their star, to icy moons hiding oceans no sunlight has ever touched, to wandering rogue worlds drifting with no star at all, a single quiet pattern begins to emerge. Wherever there is enough material and enough time, gravity seems to find a way to build something: a planet, a moon, a ring, a slow orbiting companion tracing its own patient path through the dark. Some of these worlds are violent and scorched, others cold and still, others locked forever between light and shadow, and yet each one followed the same basic, simple process: dust and gas gathering together, slowly, patiently, across millions or billions of years. There is comfort, somehow, in realizing just how much variety can grow from such a simple beginning, how the same quiet physics that shaped Earth also shaped diamond-rich giants, tidally locked twilight worlds, and small icy moons hiding oceans of their own. Somewhere among the hundreds of billions of worlds likely scattered throughout this one galaxy alone, there may be another calm, quiet planet not so different from our own, circling its own steady star, turning gently through its own version of day and night. After its brief flyby of Pluto, the same spacecraft that finally gave us a close look at that small, heart-marked world kept traveling onward into the Kuiper Belt, eventually passing an even smaller, more distant object shaped almost like two flattened spheres, gently fused together. the most distant body any spacecraft has ever examined up close. That strange, two-lobed shape suggests it formed from two separate smaller bodies drifting together so slowly and so gently that instead of colliding violently, they simply settled against one another and stuck, preserving a fragile, ancient structure that likely could not have survived any kind of faster, more energetic collision. Its reddish surface color and extremely dark, faint reflectivity mark it as one of the oldest, least disturbed objects ever studied directly, essentially untouched since the very earliest days of the solar system's formation. Reaching it required years of additional travel beyond Pluto itself, the spacecraft's signal taking many hours, even traveling at the speed of light, before finally reaching antennas back on Earth. It remains one of the most distant close-up encounters ever achieved, a brief visit to a small, ancient, gently fused world that has spent billions of years drifting quietly at the edge of everything, waiting patiently until a single spacecraft happened to pass close enough to finally see it. After spending years orbiting Saturn, studying its rings, its storms, and its many moons in extraordinary detail, one spacecraft was deliberately steered on a final, purposeful plunge directly into the planet's thick atmosphere, a decision made carefully in advance to avoid any risk of the aging probe eventually drifting into and contaminating one of Saturn's potentially habitable icy moons. In its final hours, the spacecraft continued transmitting data for as long as it possibly could, sending back readings of Saturn's deep atmosphere that no instrument had ever measured directly before, right up until the moment its signal finally went silent. It was, in a strange way, a fitting final chapter for a mission that had spent so long teaching us about Saturn's moons and rings, ending not with a quiet drift into darkness, but with one last deliberate journey directly into the heart of the very planet it had spent years studying from a careful distance. Engineers and scientists who had worked on the mission for decades watched that final transmission arrive, the last quiet signal from a machine that had shown us Enceladus's icy plumes, Titan's methane lakes, and the fine, delicate structure of Saturn's rings in more detail than anyone had ever seen before. It remains one of the more deliberate, thoughtful endings in the history of space exploration, a spacecraft choosing, in its final moments, to give one last gift of data before disappearing entirely into the planet it had spent so long quietly observing. Launched decades ago on a mission originally meant to study only the outer planets, two identical spacecraft have since traveled farther than anything else ever built by human hands, passing beyond the orbit of every planet in this solar system and continuing outward into the thin, quiet space between stars. Both are now considered to have crossed the boundary of the Sun's own protective bubble, entering what scientists call interstellar space, the first human-made objects to ever do so, carrying instruments that continue to measure the faint, unfamiliar conditions found in the space between one star system and the next. Each spacecraft carries a golden record, a physical disk holding sounds and images meant to represent life and culture on Earth, a quiet message sent outward with no real expectation of ever being received or understood by anyone, simply carried along in case it someday drifts near something or someone capable of finding it. Their power sources continue slowly fading with each passing year, and eventually their instruments will fall silent entirely, leaving them to drift onward in complete silence, carrying their golden records through the dark for as long as gravity and momentum allow, likely for many millions of years to come. It is a strange, quiet kind of immortality. Two small, aging machines, launched from Earth decades ago, continuing to travel outward long after their instruments finally go quiet, carrying a small golden record of everything we once were, drifting endlessly through the space between the stars. A newer space telescope, positioned far beyond the moon, at a stable point where the combined gravity of Earth and the Sun balances neatly, unfolded a massive sun shield, roughly the size of a tennis court, once it reached its final position. A shield designed to keep its delicate instruments cold enough to detect the faint infrared glow of extremely distant and extremely old objects. Because it observes primarily in infrared light rather than the visible light our eyes can see, this telescope can peer through clouds of dust that would otherwise block our view entirely, watching stars and planets form deep inside clouds that appear completely opaque to ordinary telescopes. It has already turned its attention towards several nearby exoplanets, carefully studying the faint light passing through their atmospheres during each transit, gathering chemical detail far more precise than any instrument before it. Engineers spent years designing and testing every mirror segment and instrument aboard, since once it reached its final position, so far from Earth, no repair mission would ever be possible the way earlier space telescopes had occasionally received hands-on servicing. Its enormous primary mirror is built from many smaller hexagonal segments fitted together, unfolding slowly and carefully after launch, until they formed one single, precisely aligned surface capable of gathering far more light than any earlier space telescope ever could. It remains one of the most sensitive instruments ever built for this kind of patient, careful search, sitting quietly at its stable point in space, gathering faint infrared light from worlds and galaxies so distant that the light reaching it has often been traveling for longer than the solar system itself has existed. A mission now on its way toward Jupiter is being sent specifically to study Europa in far greater detail than any spacecraft has managed before. Designed to fly past the icy moon dozens of times, gradually building a detailed map of its surface, while carefully avoiding the most intense radiation belts surrounding Jupiter itself. Rather than attempting to land directly, the spacecraft will use each careful flyby to study the thickness of Europa's icy shell, search for any remaining plumes of water vapor venting from cracks in the ice, and analyze the chemistry of the moon's surface for clues about the hidden ocean believed to lie beneath. Instruments aboard are specifically designed to detect subtle variations in the moon's gravity and magnetic field as the spacecraft passes overhead, data that can help confirm both the depth of the ice shell and the saltiness of the ocean hidden below it. It represents one of the most ambitious attempts yet to study, from a careful distance, an ocean world that many scientists consider among the most promising places in this entire solar system to search for the basic chemistry associated with life. The mission will take years just to reach Jupiter, and years more to complete its careful survey once it arrives. Patiently gathering data, flyby after flyby around a moon that has kept its hidden ocean sealed away from any direct human observation for as long as we have known it exists at all. For nearly a decade, one particular space telescope stared patiently at a single, modest patch of sky, no larger than a small patch you could cover with an outstretched hand held up toward the stars, quietly measuring the brightness of more than 100,000 stars within that narrow field of view, watching for the same tiny, repeating dip in light again and again. From that one small patch of sky alone, it eventually confirmed thousands of exoplanets. An enormous harvest of new worlds gathered from watching just a tiny sliver of the entire night sky. When a mechanical problem eventually threatened to end the mission early, engineers found a clever workaround. Using the gentle pressure of sunlight itself, pressing against the spacecraft's solar panels to help stabilize its aim, well enough to continue collecting useful data for years beyond what anyone originally expected. Eventually, after running low on the fuel needed to keep adjusting its position, the telescope was allowed to drift quietly, its instruments finally powered down for good, its mission complete. And yet, even after its own observations ended, scientists continue combing carefully back through the enormous archive of data it left behind, still finding new candidate planets years later hidden within readings the telescope had already gathered long before it went quiet. It is worth remembering that everything this single small telescope found came from watching just one narrow patch of an entire sky filled with stars, stretching in every direction. Meaning, the true number of planets scattered throughout our galaxy likely dwarfs even the impressive thousands already confirmed from that one small, patient corner of the search. Even the most familiar planets in our own solar system still occasionally surprise the scientists who have studied them for decades. Saturn's rings, once assumed to be nearly permanent fixtures of the planet, are now understood to be slowly raining down onto Saturn itself. Fine, icy particles pulled inward by gravity and drawn into the planet's upper atmosphere at a steady, measurable rate. At the current pace, some scientists estimate the rings could largely disappear within a time frame that, while still enormous by human standards, is startlingly brief compared to the age of the solar system itself, meaning Saturn may not have always had rings this magnificent, and may not keep them forever either. Jupiter, meanwhile, continues to reveal fresh detail every time a new spacecraft arrives to study it more closely. Recent missions uncovering shallow, dense storms lurking just beneath the cloud tops, and a deep, turbulent interior far more complex than earlier models had assumed. Even Mars, a planet crossed by rovers and studied by orbiters for decades now, still occasionally surprises scientists with fresh evidence of underground ice, unexpected seismic activity recorded by sensitive listening instruments planted on its dusty surface, or subtle mineral deposits hinting at water that once flowed somewhere new. It is a quiet reminder that even the planets sitting closest to us, the ones we have studied longest and know best, still hold details we have not yet uncovered. Patient worlds willing to reveal a little more each time we manage to look closely enough. And so our slow journey through this quiet gathering of worlds comes to its end for tonight. We have drifted past a sideways planet locked in decades-long seasons, past a scorched twin of Earth spinning backwards beneath sulfuric clouds, past moons hiding oceans no sunlight has ever reached, and past small, icy wanderers drifting alone with no star to call their own. We have watched storms larger than entire planets spin quietly for centuries, and machines built by human hands travel farther than anything else we have ever sent outward, carrying a small golden record into the dark long after their own voices finally fell silent. Every single one of these worlds, whether close by or hundreds of light years distant, whether confirmed with certainty or still only gently suspected, followed the same unhurried, patient process, dust and gas slowly gathering together under nothing more than the quiet, steady pull of gravity. There is something calming in that thought, that the same simple, unremarkable physics responsible for Earth beneath your own feet also shaped diamond-rich giants, twilight worlds locked forever between light and dark, and small icy moons hiding entire oceans of their own. Somewhere out there, among the hundreds of billions of worlds likely scattered throughout this one galaxy alone, more are still forming right now, quietly gathering themselves together in the dark, patient and unhurried, exactly the way every planet we have visited tonight once began. Not every exoplanet system arranges itself in the calm, orderly way our own solar system did, with small rocky worlds close in and large gas giants settled comfortably farther out. In some systems, a massive gas giant appears to sit exactly where a small rocky world would be expected, suggesting it formed much farther out and slowly migrated inward over millions of years. drifting closer to its star through gradual gravitational interactions with the disk of material it was born from. As a giant planet migrates inward like this, its gravity can scatter smaller planets out of its path entirely, flinging them into wide, eccentric orbits, ejecting them from the system altogether, or in some cases, pulling them along into unusually tight, resonant orbits of their own. This kind of planetary migration may explain why so many of the earliest exoplanets discovered turned out to be enormous gas giants sitting shockingly close to their stars, a configuration no one expected before these discoveries began. Since nothing in our own solar system had ever suggested planets could wander so far from where they first formed. Some systems appear to have experienced this kind of upheaval only once, early in their history, before settling into a new, stable arrangement that has persisted quietly ever since. Others may still be in the process of shifting even now, their planets slowly drifting closer together or farther apart, an entire system rearranging itself over timescales too slow for any single human lifetime to notice. Patient architecture still quietly settling into whatever final shape it will eventually hold. Every one of these worlds we have wandered through tonight began the same simple way. A thin disk of dust and gas slowly circling a newly formed star. Tiny grains gently colliding and sticking together over countless quiet years until something large enough to call itself a planet finally took shape. It is a process built from patience rather than force. Gravity working so gradually that from any single moment, nothing seems to be happening at all. And yet, given enough time, given enough dust, given enough stillness and quiet persistence, entire worlds emerge, spinning, settling slowly into the shapes and rhythms we have spent tonight exploring one by one. Before we close, if this quiet journey through distant worlds helped you rest, you are always welcome to like the video and subscribe for more journeys like this one. And now, let your thoughts settle. Let the planets keep their slow and steady turning, and rest easy, knowing the universe will still be here, quietly unfolding whenever you return to it.